Welcome to Lesson 2 in our study of rational numbers, Module 2. And the title of our lesson today is Using the Number Line to Model the Addition of Integers. Okay, I'm sure you're experiencing a little breath of relief with this unit, but please, despite how easy it looks, please don't take it too lightly, because there are some formalities of the way we record things and write things that are very important to continue to do correctly. Okay, so I will point those things out as we go. Anyway, to begin here, exercise 1, real world introduction to integer addition. Okay, and this whole idea of real world. All right, answer the questions below. A, I'm going to have you do these questions. Let's do this one at a time. Let's go and do A first. So suppose you received $10 from your grandmother for your birthday. You spent $4 on snacks. Using addition, how would you write a number sentence to represent this situation? So go ahead and pause the presentation and do this on your own, and come on back and we'll look at it again. And of course you thought that was very simple, but if your answer does not look like this, I'm going to tell you right now that it is not in the correct format that I would like to see you do. Okay, I would like to see you adhere to this format, and how this might be different is probably this part right here. Okay, this part right here I'm thinking is different on most of your papers. Okay. Now, I'm sure most of you wrote 10 minus 4 equals 6. And in another day and age or another time of your life, that would have been correct. But it's not perfect any longer. Okay, we talked about doing away with this idea of subtraction, taking away this whole subtraction symbol and just replacing it with a plus sign, so 10, and then plus, because we're always taking the sum of something. So then plus, but a plus a negative 4, and that equals 6. Okay, so this is how I would like to see it all the time. Remember that in the future. Okay, so let's go ahead and do B. So now B, use this number line there. How would you model your equation on a number line to show your answer? So go ahead and do that and come on back. Okay, now when it comes to modeling your equation on the number line, hopefully you did something like this. Start from 0, okay, because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the $10 you got from Grandma, okay, right? And then, I'm just using a red. I'm going to use red because I like using red. Then if I'm going to take away or have a negative, because I have a negative 4 now because I'm spending 4 on snacks. 1, 2, 3, 4. Okay? So here's my negative 4. There was my positive 10. Actually, I don't need a positive sign. Remember that? There's your 10. Okay? And where do you end up? You end up at 6 right there. Okay, so hopefully it looks like that. You know, real-world situations can be modeled with equations that are represented on a real number line. Now this positive 10 in this case represents $10 given as a birthday gift. Okay, because this $10 here, this represents a gain. Okay, it represents a gain of $10. Okay, and that 4, that negative 4, it represents $4 spent on snacks, because it is what we refer to as a loss. Not necessarily a loss, but I mean it's an expenditure. Okay, yeah, but I guess you do lose the money, but you're getting snacks for it. Okay, so if you gain 10, you lose, take away 4, you're left with 6. So again, some maybe new terminology to you, this idea of gain and loss. Okay, so here in example 1, modeling addition on the number line, it asks you to complete the steps to finding the sum of -2 plus 3 by filling in the blanks. And then you're going to go ahead and model that number sentence using straight arrows called vectors on the number line below. This word here, vectors, is a word we'll talk about a little bit more. It's not one of our terminology for this chapter, but it probably should have been. But anyway, what we will do is go ahead. We're going to fill out this A through E with these steps. Let's do this together. And again, you're thinking about this. We're finding the sum of -2 plus 3. Okay, -2 plus 3. All right. So we place the tail of the arrow. Now, I should probably explain that to you, but a vector is an arrow. Okay, and you're going to see this when you you talk when you do your physical science, physics. When you talk about motion and force, we use these arrows called vectors, and they usually are the way they're modeled is the longer they are, or the larger they are in physics when you're writing about forces. And I hope this isn't confusing, but the more they're worth, or the larger the magnitude. In any case, we will see this when we draw on the number line below. But a vector is a straight arrow like this. It doesn't need to be going right always. It could also go left. Okay, depending whether you're adding or you're taking away. Okay. So you're going to place the tail of the arrow on 0, okay, because this is what we start off with. Any kind of finding of a sum, we're assuming that we are starting with 0, okay? So then you're going to draw the arrow 2 units to the left of 0 and stop at -2, okay? The direction of the arrow is to the left, since you are counting down from 0. Okay, we're talking about counting down. Of course, we're going to go to the left. Start the next arrow at the end of the first arrow, or at -2, because that's where we are. Draw the second arrow 3 units to the right, since you are counting up from -2. Now, if you think about it, you may know it already, but you're going to stop at 1. Okay, so let's go ahead and take a look at what that looks like on the number line. Okay, so here's your number F here. Let's do what we just did. We're going to draw some vectors. You can do this with me, and then I'll let you. Well, at some point you'll have to do this on your own. So, anyway, what you're going to do here is you're going to start from 1. Start from 0. You're going to go to the left, -2. Okay, 2 places, because it is we are modeling now -2 plus 3. Okay, so we started at 0, went to the left 2 places. Okay, and then we are going to go to the right, starting at -2, because that's where I am right now. We're going to go 3 places, and you can see there 1, 2, 3, and that puts us at 1. Okay, that puts us at 1. Now these arrows are called vectors. Okay, we call these vectors, and this idea of vectors will, again, like I said, a lot of this stuff seems easy, but one of the real reasons we do it is we're doing this now and taking our time doing it is so we can talk about these things such as vectors and about how to actually write our problems with negative numbers more correctly, as you see what's happening in letter G. So let's look at letter G right now. If you need to pause at any time, always feel like you can. these lessons aren't going to take half as long as the ones from Module 1. Okay, so G says repeat the process from parts A to F, that's what we just did, for the expression 3 plus negative 2. Okay, 3 plus negative 2. All right, and you can see again this is one of those areas of understanding that may take some time, but this idea of actually adding a negative 2 instead of just subtracting 2. Okay, all right. So why don't you go ahead and do that? Go ahead and use vectors to complete this this expression right here. Okay, and then come on back. Okay, welcome back. You can take a look down here to see what I did. Hopefully you did something very similar. Started at 0, 3 units to the right because it is positive in nature. Okay, and then I added, quote unquote, added a negative 2. So that just means very simply moving 2 to the left, and there I sit at the same exact place, okay, at 1. And you can see how these now are the same, okay, these two, because what they do, they are the sum of a negative 2 and a positive 3. Same way here, negative 2, positive 3. This idea of a sum, and they're going to leave us in the same exact place, okay? Now, oh well, here I guess H is going to ask this question. So what can you say about the sum of negative 2 plus 3 and 3 plus negative 2? Does order matter when adding numbers? Why or why not? Well, in this case, the order does indeed not matter when adding numbers, okay? All right, and actually, in all cases, because this is one of our another terminology word that we have at on the terminology sheet at the website. But this addition is what we say. We say addition is commutative, commutative in nature. Okay. And let me go ahead. I'm going to go grab the terminology sheet just to show you what it looks like, and I'll be right back. Okay, so here's our terminology sheet, and like I had I told you before, it resides at the website under the terminology tab, so you can go there and find it there. I also plan on handing this out in class. But anyway, here at this terminology sheet, you can see the definition of commutative property. Okay, and commutative property applies to both multiplication and addition, and not to division nor subtraction. Okay, and if you read here, here's a definition. In mathematics, an operation is commutative if changing the order of the operands, and an operand is just a number or whatever that is a term that is in a a sentence of some sort, does not change the end result. Okay, so changing order does not change the end result. And again, like I had said before, addition and multiplication are commutative, while division and subtraction aren't. Okay? All right, so if I hadn't answered this question yet, I think I did, but anyway, not that one. But does order matter when adding numbers? And that answer is no. Okay, and that's because addition is commutative in nature. Okay? All right, let's go through. We have example 2 here now. Expressing absolute value as the length of an arrow on the real number line. Now, real number. It's like real number line. It's not like real number line, like there's a fake number line. No, it means the real number line. Okay, we're talking about real numbers here. Okay, and again, if you don't know what that, what the definition of that is, you can go ahead and look on the terminology sheet as well. Or actually, we can look right here. We're going to have a lot of time. So let me go grab that again, and let's look at the definition of what a real number is. Okay, so here we have the we have our terminology sheet again, and we have real numbers, okay? So, all numbers on the number line. Real numbers are any number that could actually exist on a number line. So, now read this along with me. This includes, but is not limited to, positives and negatives, integers and rational numbers, square roots, cubed roots, even pi, okay, 3.14, blah, 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 etc., okay? Now, real numbers are indicated by either this R or this other R, kind of fancy-looking R's. This one just fancy schmancy. The other one, I do believe, is Greek, probably a Greek from the Greek alphabet. So, yeah, that's what real numbers are. They're pretty much everything. Now, there are other numbers that will not, that cannot be on there, but it's pretty limited. The only numbers truly that can't be on a number line are something called imaginary numbers, so we're not going to worry about that right now, okay? But yeah, real numbers is a pretty wide lot of numbers. Okay. Okay, so here we are back to this problem. How does absolute value, again, if you remember, absolute value determine the arrow length for negative 2? Okay. Of course, I'm hoping anyway. I think we talked about absolute value already in part 1 or in lesson 1. But if not, let's go ahead and look at this now together, and then I can have you do B yourself. Okay. So again, how does absolute value determine the arrow length for negative 2? Now, negative 2, again, we start at 0 and head down to negative 2. Okay. Now, how does absolute value determine that? So, absolute value, as we know, hopefully we know, deals with distance. Okay. And in this case, distance from 0. Okay, distance from 0. All right. And the distance from 0 here is actually 2 units. Okay. So absolute value, it determines the arrow length for negative 2 by being 2 units. Okay. So the absolute value is 2 units. And of course, the absolute value doesn't, I mean, it means nothing that we're talking about a negative number here. Okay, the only thing that changes here is that the arrow, our vector, is moving to the left. Okay, so we go left 2 units. You know, our absolute value is still 2 units. Okay, but we're just moving to the left. Now B, I want you to go ahead and do this yourself. Think about it, and when I come back, we'll talk about it. But again, it's similar. So, how about this? How does the absolute value determine the arrow length for 3? Okay, yeah. So for B here, again, very similar to the one up top, but in this case, the absolute value is 3 units because the number is 3, and the only thing that changes is it is to the right. Okay, to the right because it is positive in nature. So the way I would write these, I would write this as absolute value of 3, and that equals 3. And if you know the absolute value sign, those 2 lines on either side of the number. And up here is it's negative 2, again with the absolute value, and that equals 2. Okay, and again these 2 both refer to distance. Okay, and distance here, distance from 0. Okay, on a number line. Alrighty. Okay, now here is C. C, I want you to put this into words. And again, you know how in these standards, more and more want you to be able to express yourself in writing. So let's go ahead, and I want you to just write an explanation. You don't need to draw a number line here, but how does absolute value help you to represent negative 10 on the number line? Go ahead and try to put that into words. I know this is, for some of you, this is an absolute grind, but it's good to get practice. Okay, so go ahead and give that a try. Come on back and See how your explanation compares to mine. Okay, let's see how yours compares to mine I wrote here. So the absolute value, and again the question, how does absolute value help you to represent -10 on a number line? The absolute value can help me because it tells me how long my arrow should be when starting at 0 on the real number line. Okay, and the absolute value of -10 is 10. Okay, so I know I have to move 10. And the idea that it is -10 tells me I am moving to the left. Okay? All right, so exercise 2 says create a number line model to represent each of the expressions below. Let's see, we have A, B, and is that it? Yeah, A and B. Okay. So go ahead and do those, and come on back, and you can take a look at the ones that I created. Okay, well, here are my answers, and I'm sure you have similar answers. Okay, again, absolute value using those vectors. Hopefully, everyone is using the arrows, the vectors, to portray these moves. Okay, alrighty. So let's continue on. Here's example 3. Finding sums on a real number line model. Okay, so what we want you to do here is now it's like, see, here's also how these new standards or this curriculum that we're doing. We're always trying to look at it in 2 ways. You know, create your own, and then to use something someone else has created, like this one right here, like this number line here, the diagram, and then you're going to actually pull information from it. So you know, extract information from it, because using a diagram to get information really, really very important. Okay, so what I want you to do here is to go ahead and write an equation to express the sum that is expressed or is represented in this diagram. Okay, so go ahead and do that, and come back and tell me what you. Oh, don't tell me anything. You can't tell me. You can't speak through the computer. But and take a look at what I've written down. Well, actually, I haven't written anything yet, but I just wanted to go ahead and do this in front of you. And hopefully, again, you've noticed that you start from that bottom line. This is always a line that comes first, or I'm sorry, not line, but the arrow. Okay, so you're going to write an equation to express the sum. So you can see right here we have a 5. Okay, because we've gone 5 from 0. Okay, 5 that way from 0. Okay, now from that point of that 5, you see we've gone back -2. Okay, right there, gone back 2. But again, these are sums. So when you have a sum, sums are addition. Okay, sums are addition. So we're going to put plus, and hopefully you did this, -2. All right, and then we got to that point. We're now at 3, +3, and then we went to the right another 3. Okay, so then we added 3. Okay, and since it is an equation, okay, really, really important, it's not an expression, okay, it's an equation. An equation means that there is an equal sign, okay, so just always remember something good to know. Equations include equal signs, and this is actually at the terminology page as well, equal signs, okay, and there may be more than one, okay. Anyway, so if we do add all this together or sum these, we get 6, and we know because we've landed there on the number line. Okay. Alrighty. So if let's just look here now. B wants you to actually we're going to refer to the integer game. Okay, from lesson 1. All right. So if we were playing the integer game, what 3 cards are represented in this model? Okay, what 3 cards from the integer game are represented in this model? In this case, let's say these are the first 3 cards you were dealt. Which 3 cards would you have been dealt? Okay, and I'm pretty sure you can get this. Of course, we would have gotten the 5. All right, then we would have been dealt a -2, and then we would have been dealt a 3. Okay, alrighty, and how did you know? Of course, you can tell just based on the equation you wrote, okay, or on the the number line, the way the arrows are moving. Okay, alrighty. So C asks you, in what ways does this model differ from the ones we used in lesson 1? Now, if you want to go back to those that we used in lesson 1 and take a look, this whole way of modeling, and when we refer to this model, we're talking about the vectors, okay? This vector model. How does this vector model with the arrows differ from what we've done in the past, okay, what we've done before? And again, I'm just going to cut to the chase. If you want to pause right now, you can and go look. But if you do remember, in lesson 1, like a movement of 5 units was shown. If you remember, with separate hops. Okay, if you remember that. Hold on one second. Let me go get a. I don't need it really. I'm just going to draw it here. I like when the number lines are nice, but I'm just going to draw it here. If you remember, in lesson 1, we looked at if we had a +5, okay, we would have gone 1, 2, 3, 4, 5. I actually did that once in this lesson as well at the beginning. Okay, we showed it as separate hops. All right. In this case, right now we are showing 5 units in one total movement with a straight arrow. Okay, and as you can see right here, let me just clean this up a little bit. It's kind of messy, but here is here's a +5 right there. As you can see it, it's one straight shot. Now they are the same because they do represent the same total movement. Okay, but in this case it's more of a counting. This is like more of a counting model, whereas the other one is what we call a vector model. Okay, a vector model. How about D? Can you make a connection between the sum of 6 and where the third arrow ends on the number line? Okay. Can you make a connection between the sum and where the third arrow ends on the number line? And yeah, I mean, this is pretty clear, huh? I mean, if you the connection is that is the total. Okay, that is the sum. All right, because the sum, the last arrow ends at 6, +6, and our final position. That's our final position. Okay, and it is 6, and these are going to be the same thing. So wherever your final arrow ends, that should be the sum of your problem. Okay. All right. So E asks, would the sum change if we change the order in which we add the numbers? For example, so yeah. So right here. How about if we did that? What was our original one was 5 plus -2 plus 3, right? It was 5 plus -2 plus 3, and that equaled 6, okay? So would the sum change if we changed the order? Okay, and that's the big question, and we've answered that already. Hopefully you do remember, and hopefully you will never forget, okay? Well, if you just go ahead and match these numbers, here's our -2, here's our -2, here's our +3, here's our +3, here's our +5, here's our +5. Okay, so the answer is no. No, the sum would not change. Okay, the sum would not change because, remember, we have the property. The property is called the commutative property, which we had talked about already, and we have defined on the terminology page. Yes, commutative. It does not matter the order. And let's just go ahead and do it. So -2. Okay, so if we did it here, let's just do this new problem. We'll go -2. Okay, -2, and then we went positive 3, and then positive 5, we end up in the same place. Okay? So it doesn't matter. And again, this was negative 2. We did negative 2 first. We did positive 3 first, and then positive 5 last. Okay? It doesn't matter. Order does not matter, because addition, like its partner, multiplication, is commutative. Order does not change, would not change the sum. Okay. Looks like hold on a second. Looks like I've missed one problem. Oh, hold on a second here. I missed this one down here. Let me get rid of this messy mess here. Okay. Let's clean all that up. I don't like it. Alrighty. So yeah, last question here is: would the diagram change, and if so, how? Well, I guess I got ahead of that one, huh? Yeah, the diagram does change, and you can see diagram changes. Starts left, heads right. The first diagram, went right, left, right. Okay, but everything still ends at 6. So yeah, the answer to this question would be yes. Because the order of our moves would change. Okay, but that's it. Nothing else. Some would not change. All right. Okie doke. Okay, now our exercise 3. Exercise 3, yeah, if we were in class right now, and if you were in class with me every day, which would be a great thing, I think, we would play the integer game right now. But I'd like you to go ahead and do that. If you want to pause, play a couple rounds of the integer game with your parent, teacher, sister, brother, whomever. Okay, so go ahead and do that. Pause, play around, and come on back. Okay, so in closing, I just want to ask you one question here. So what does, now in your own words, I want you to go ahead and just write this down somewhere in your binder, okay, and then come on back and see what I've written. What does the absolute value of a number line tell us? Okay, and it can be many different things. I'm thinking of maybe 2 or 3 different things already, okay, in my head. So, so come on back, think about that question, and then come on back. Okay, so here are a few things that I came up with. If we're talking about a number line, on a number line, it tells us the length of the arrow. Okay, on a or the arrow or the vector. Okay, an arrow or vector. Okay, length. Now, in general, what absolute value tells us is the distance the number lies from 0. Okay, so these two ideas, length and distance, are indeed related. Okay, and as you know, they move in one dimension. Okay, they're both one-dimensional measurements. All right. Okay, so that's pretty much it from my end here. I don't know. Maybe you guys have thought of some other things, and I'll probably think of some other things as soon as I shut this off. But okay, so let's go ahead. Here's our lesson summary. Okay. On a number line, arrows are used to represent integers. Okay, they show length and direction. Okay, length and direction. Again, positive numbers moving to the right, negative numbers moving to the left. Okay, the length of an arrow on the number line is the absolute value of the integer. Okay, and here we go again. Length of arrow on a number line, absolute value of the integer. Okay, now adding several arrows is the same as combining integers in the integer game. Okay, and the sum of several arrows is the final position of the last arrow. Okay, it's kind of like your destination. If you're walking somewhere, let's say you have to walk to, you walk to the store, walk to the candy store, and then you walk back home. Okay, you've pretty much, if you that's real interesting actually when you get into physics and you talk about motion, this idea of your displacement. It's really, really interesting. And again, I don't want to confuse many of you, but let's just say you're walking to the store, and it's like, let's say it's 5 miles. Well, 1, 2, 3, 4, 5. Let's say it's 2 miles. Okay, 2 miles. That's 5 miles. That's pretty far. 2 miles. That's even far. So 2 miles. You walk to the store. So you've actually, you walked this 2 miles, and then you walk back 2 miles. Okay, it's a -2. Where do you end up? You end up at 0. Okay, here you are back where you started. Okay, so in a true physics sense, you've actually okay, I'm sorry, there's a little abrupt move there. Gosh, my my laptop keeps disconnecting, so because I'm not doing a lot on it. But anyway, just wanted to continue this, and I was just starting to talk. I don't know how much you actually heard of this, but I was talking about going to the candy store, and you went up 2 miles, you went and there, and then you came 2 miles back home. And a pure sense of physics, you've actually displaced, you've gone nowhere pretty much, okay? Even though you've done a lot of walking. Yeah. But anyway, that's interesting because that just shows you how this works on a number line, okay? This idea of, +2 and then a -2, taking that away, and you end up at 0, okay? Anyway, this whole final position, okay? So your final position, that is the sum, okay? So in this case, your sum of your how far you got away from home is 0. Okay. Whew. Anyhow, yeah. Go ahead and do your problem set, do your exit ticket. Any questions you ever have for me, call me. Please study that terminology and play that integer game. Okay.